Let's begin. We will pick up from the normal distribution where we left off last time. Also, if you're interested in narrating the next story, please let me know. Currently, Elijah is indefinitely subscribed until he graduates. Did you hear the final product? I added some sound effects on YouTube. You know, I added some echo and like I modulated his pitch a little bit on, you know, some of the pieces. Anyway, so yeah, go support him, like the video, put good comments. If you don't like it, just don't put the thumbs down, okay? Just, you know, don't watch it, right? If you don't like it, don't watch it. All right, so we'll continue with the normal distribution. We might not finish the entire chapter on continuous distributions. Just to give you a reminder where we're at, we're almost done with probability. Remember, we talked with statistics, we got to do descriptive statistics and then inferential statistics, which are a pretty powerful tool. But to go to inferential, we need probability distributions. And to understand probability, we are in this mode now, in this unit, looking at probabilities. So we're almost done. We still have one chapter or 1.5 chapters. You know, taking these probability distributions to the next level, and then we'll go full-blown on inferential statistics. So today we will be using Python, finally, Python. So you got my announcement last time. Most of you have it installed. For those who did not, from numerical methods, obviously. For those who did not take numerical methods with me, I hope you had a chance to install it, or if you're doing 1703 at this time, you're already using it. If not, let me know and I'll come and help you. We can find an online portal where you can just kind of try things out until you get things installed. Does anyone not have Jupyter Notebooks installed? Okay, great, perfect. Okay, so the reminder about the beautiful normal distribution is that initially De Moivre in 1773 concluded that distribution as he was working with the binomial distribution. And later today, we will show that the normal distribution is a great approximation to the binomial distribution for under certain conditions. And so you actually, when we plotted the binomial, it does look like a bell curve, right? So under certain conditions, we can totally use the normal distribution. Gauss rediscovered it. Sometimes you will hear the normal distribution called a Gaussian. When I distinguish both by the following. When the distribution is normalized so that its total integral is 1, in other words, all the probabilities add up to 1, then I call that the normal distribution. When it doesn't add up to 1, because you can manipulate the coefficient of that distribution, as I'll show you later, then I call it just a Gaussian. It still looks like a bell curve, but it doesn't integrate to 1. So the probabilities, so it's not a probability density anymore. It's just some other distribution. So you would call it a Gaussian. So that's how we distinguish the two. But for a PDF, for a probability setting, call it the normal distribution. Laplace was the guy who finally figured out what no one had seen about the importance of the normal distribution in what he called the central limit theorem. And what he discovered is so universal, and is in that repeating events that you average out and you repeat and you average, you repeat and you average. I'll give you an example. Those averages will follow a normal distribution. Okay, those averages will follow a normal distribution. And initially the idea started by scientists. They were doing measurements in a lab, measuring concentration of some reactant or radioactive decay, for example. They'll do the experiment on day 1. They take 50 measurements, they average them out, and they say, okay, you know, today this is picocuries per unit volume or something. That's it. Next day they come and take a measurement of the same experiment and take measurements, average them, and they do the same over and over again. Or different people come and do those measurements, they average them. Those averages were normally distributed. Turned out they were normally distributed. They were not identical every day because there's, you know, things are changing. There's different humidity, different temperature, the apparatus is shaking, and so on and so forth. It's aging, etc., many factors. But those averages were normally distributed. And turns out that this is a universal pattern in life and in nature. And here's another example that I gave last time. You roll a die 100 times, or 5 times, or 1,000 times. Call that one experiment. Okay? Then you record the average of all outcomes. So on the first time you got 2, the second time you got 3, then 5, then 6, then 2, then 1, 100 times. Take the average, sum all of those up, divide by 100. That's the result of one experiment, the average outcome of rolling the die. Then you repeat that experiment. Again, roll it 100 times, another one, and 100 times, and 100 times, average, average, average. Those averages, if you plot them, versus on the x-axis, if you put the experiment number, they look like a normal distribution. It's incredibly universal. Okay, we will call that the central limit theorem. Before I call it that, you might ask, when do we average? Like, when is a situation where we average? In experimental settings, in scientific settings, in engineering settings, you are averaging all the time, especially when you go take out a measurement. We did this exact thing when we did the Utah Symphony study. For those who took numerical methods, you saw that in the beginning of my lectures in numerical methods. I showed you the simulation of the Utah Symphony and the airflow during COVID. To figure out the airflow, we had to climb on like a 30-foot, not climb, we had like this lift, 32 feet high ceilings. We went up and we were taking measurements of the airflow in these intake vents here, these inlet vents. And so, you know, you could take the measurement on the left, on the right, in the middle, etc. So we took a few measurements, 15, 20 measurements, and we would average those measurements, right? And say, okay, the airflow is on average, or the speed in this is on average 0.5 meter per second, okay? But those measurements, now the measurements themselves are not normally distributed, but the average would be normally distributed if we were to take it over and over again, okay? Now, that is called the central limit theorem. That will actually be the foundation for inferential statistics. So we will cover the central limit theorem in the next chapter and how all averages, all distributions tend to the central limit theorem. All right, are you ready to see the normal distribution, how beautiful it is? This is the formula for the normal distribution. We give it a symbol, capital N, in contradiction to what we've done so far, because we used the lowercase to designate the PMF and the uppercase to designate the cumulative distribution. In this case, the normal distribution is usually they use also a scripted N, but you know they call it N. I want to follow the standard. So a normal distribution is given by N, and it has 3 arguments. X, the value, this is a PDF, probability density function. The density, the probability density at the value X, and mu and sigma squared, those are 2 parameters for that distribution. It looks like an exponential function with a squared exponent and a negative sign in front of it. Those mu and sigma, now x goes from minus infinity to plus infinity. Okay, could be negative, could be positive, doesn't matter. Right, now obviously the PDF is a positive value, so when you plot this, it's going to be strictly positive. Guess what? Mu is the expected value, so that's the mean of the normal distribution. So you could say, I want to build a normal distribution with a mean value of 0.65. You put 0.65 where mu is up in the exponent, and you guarantee you're going to get that. And guess what, too? Mu could be negative or positive, because x can be negative or positive. And sigma is what? The standard deviation. So now I can entirely specify a normal distribution just by knowing the mean and the standard deviation. So you could say, I could ask you, go build me a normal distribution with a mean of minus 0.6 and a standard deviation of 3. You just plug in 0.6 in place of mu and 3 in place of sigma, and you plot it, and you get a normal distribution, PDF, that has this mean value and a standard deviation. It looks something like this. Okay, it looks something like this. These are 3 different distributions. If you start with these 2, they have the same mean, equal 5, but this one has a standard deviation of 1, or variance of 1, and this one has a variance of 4, or standard deviation of 2. So you notice how the standard deviation, as we learn, it shows how much the data is spread around the mean. This is another normal distribution, looks like a bell, right? Okay, and this has a mean value at 15 with a standard deviation of 1, okay? Now, this distribution goes to infinity, but it's always strictly positive. It asymptotes to 0. at plus and minus infinity, but it never goes negative. It never crosses the x-axis. Okay, never crosses the x-axis. All right. The following results are true for any normal distribution with any mean and any standard deviation. So super powerful result. And that's the result we learned earlier, that 68% of the data or the probability lies within one standard deviation from the mean. So as you could probably tell already, and this is going to be maybe a quiz question or an exam question, is that if you change the mean, it's going to change the location of the distribution. And we'll see later that it is centered. One of the properties of the normal distribution is that it is always symmetric around the mean value. Okay, so within one standard deviation of the mean, for any mean and sigma, for any normal distribution, you get 68% probability that you're going to fall in there. Within 2 standard deviations, you get 95% probability. And within 3 standard deviations, you get 99.7% probability. Okay? Now, why are these probabilities? Because they're the area under the curve, like we studied about the PDF. Okay? Like we studied about a generic PDF. And we can express those by saying probability that x between mu minus sigma and mu plus sigma is 68%, mu minus 2 sigma, mu plus 2 sigma is 95%, and so on. Okay? And you can compute those. We'll probably try them in Python and the tables that we will learn a little later. Okay? All right, some of the properties is that the normal distribution looks like a bell, and it's symmetric about its mean, always symmetric around the mean, okay? About the mean. So if you draw a vertical line around the mean, the left of the distribution is going to look exactly the same as a mirror image of the right of the distribution. It's completely defined by the mean and standard deviation. That's it. So now if you know you're studying something and you say it's distributed, it's normally distributed, and it has this mean value and this standard deviation, you can build the normal distribution instantly. Just plug in mu and sigma. Very useful. The total area under the normal distribution should equal to 1 exactly. Okay? That's expected because this is a PDF. It should, by definition, integrate to 1, and we can verify that numerically. The x-axis is a horizontal asymptote for the normal distribution, like I said. The normal distribution never crosses the x-axis. It asymptotes to 0 at plus and minus infinity. Now, I told you about the Gaussian. So if I were to remove 1 over sigma square root of 2 pi, I call that a Gaussian. Okay? It still looks like a bell curve, but it's not normalized to give you an area equal to 1. But it will still look like a bell curve. Okay, so sometimes I'm building initial conditions in my simulations, and I just want to use a Gaussian. I don't care about the mean and standard deviation. I just plug in a Gaussian e to the minus x squared over 2. I call that a Gaussian. It's a special case of the normal distribution, or the other way around. The normal distribution is a special case of the Gaussian because it's normalized to 1. All right. Are we ready for this? Yay! It's like been such a long time we've missed this. So for those who didn't take numerical methods, in numerical methods, I always we interrupt the lecture in the middle, and we had this thing called Pythonification, which is essentially, I even forgot the definition now. So it hasn't been a semester already, I forgot it. So it's the process of taking something and converting it into code with Python, okay? So now in this course, yeah, we're using Google Sheets or Google or Excel on some problems, right? But for more serious stuff, we need to use Python. And this would be the segue to get us started using Python. I spent days and nights trying to figure out what is the best tool that I want to teach you in Python, what is the best library that I want to use to do statistics in Python. You've heard Pandas, scikit-learn, NumPy. We can do a lot of stuff with NumPy, but unfortunately, it's going to take a lot of work to build these distributions and define means and moments, etc. So we're not going to use NumPy to do our core statistical analysis. We need something that has some fundamental statistical tools in it. Like I wanted to have a built-in normal distribution. I wanted to have a built-in uniform distribution or binomial distribution and so on. So Pandas, I think, is an overkill. We might get to it at the end of the semester, but it's too many knobs, and you'll spend your time wasting your time trying to learn how to operate Pandas before you actually start doing actual statistics. The tool that I think is going to be appropriate for us and productive is going to come from SciPy Statistics Library. It's a lightweight library. It doesn't do all sorts of statistics, but it gets the job done for what we want to do and for most of the things you want to do, and gives you an introduction to. It's not simple. It can do complicated stuff. As we'll see, it will do everything we need to do. So we will be using that. We'll start with it and see how it goes. I think it's going to be a successful journey with SciPy Stats. So we will have to import these two things. The first one is from SciPy import stats. So that brings us the entire stats library. Now, from the stats library, you will see things like I'm importing a normal distribution, an exponential distribution, and a uniform distribution. We will learn more as we go what distributions we can import. You can obviously read the documentation, the terrible documentation of scipy.stats. Unfortunately, it's not very well documented, but you can find your way around it for finding all sorts of probability distributions. Okay, so let's grab our Jupyter notebooks, and our first example is going to be to just build a normal distribution from scipy.stats and plot it, and then try to ask it what is a probability, of getting something, right? Of the CDF, for example, or the PDF of it. Okay, so get your Jupyter notebooks open, and in this case, we're going to need a slightly different boilerplate. So also for those who are not in numerical methods, the boilerplate is going to be the common imports that we will use in all our Jupyter notebooks moving forward. All right, so now the same requirements apply in this class as the requirements in numerical methods for you to include text and discussion in your notebooks. For those who are doing this for the first time with me, your Jupyter notebook submissions for homework need to include appropriate discussions using text cells, printed out results from your routines do not count as answers. You have to interpret the answer. You have to copy it and paste it in your text cell and interpret it. The only thing that's acceptable as something that's coming out directly from the code is a plot. Okay, so a matplotlib plot, that's acceptable. Otherwise, you have to interpret your code. We will not read your code. We will not debug it. We will assume that it just works. If it doesn't work, please come to us so we can help you make it work before you submit it. Okay? It's not going to be as heavy coding as numerical methods. Okay, so be a little bit less intense as numerical methods. Okay, so what I want to import, I'm not going to copy. I'll just do it with you by hand so we can take our time. All right, so we will start by import matplotlib.pyplot as PLT. So now, you know what this is fully by now, and the little trick that I like to use is the matplotlib magic. So I get high quality graphics and just copy and paste this config inline backend dot figure format is equal SVG. Don't ask me how I got this. I just found it, in the desert. So, it makes beautiful plots in high quality graphics. In Jupyter notebooks, we're going to need NumPy. Import NumPy as MP. So we're just giving them nicknames so we can use them easily. And then from SciPy, import stats. And then from scipy.stats, import norm. Now, norm is the normal distribution that comes by definition from scipy.stats. So scipy.stats. Okay, so if you want, you can look up the documentation on scipy.stats, a bunch of statistical functions. There's a lot of things going on, but you can find all of these distributions here. This is, for example, exponential for the exponential distribution. There's a gamma distribution. We haven't learned about any of those, but there's a lot going on, and you can read about those in the documentation itself. There's a lot. And see, this is the normal distribution here. So I'm going to import this normal distribution from SciPy, okay? All right. So now my first objective is to just plot this distribution. And I truly believe in just coding by example. You don't need a computer science course to learn how to code. You don't need to learn the theory of programming. As engineers, we're using coding as a tool, probably going to be obsolete in 10 years with AI doing the work for us, but you still need to understand the concepts. It's more important to me that you understand what you need to do in the code rather on how to do it specifically, okay? Because things change all the time. Every year, there's new interface for these codes, so you have to Google it and learn it. I'm not going to occupy disk space in my head to memorize this, but what is going to occupy in my head is how I need to do things, what I want to do. So to plot the distribution, I need values on the x-axis, and then I need to create the y values, okay? So let's start with creating a bunch of x values with our favorite linspace. So x is going to be mp.linspace. Let's go from -10 to 10 and put 300 points. So, and then if you're in doubt, what do? Print it out. Yep, when in doubt, print it out. So print x, and then you get a bunch of values that are equally distributed from -10 all the way to 10. There's 300 values of those, okay? And this would be a NumPy array, all right? Great, so we created our space. Now, let's build a normal distribution. Okay. Now, typically, there are a few ways to use SciPy stats to operate with probability distributions. The cleanest way that I will recommend you adopt, and the one that I will teach you, is as follows. So, first, let's set a mean value. Let's say I want a normal distribution with a mean value of 1.5 and a standard deviation of 2. Okay. Now I'm going to go and call the norm routine from SciPy, or the norm object from SciPy. Now, unfortunately, if you type in norm and open parentheses and you press Shift-Tab, that should give you the function signature. If you remember, in numerical methods, we use that to understand what's going on. Unfortunately, it's utterly useless because all you see is args and keywords. I'm like, where do I specify the mean value or the standard deviation? That's what's bad about SciPy.stats. It's not the only bad library documentation out there. So you have to dig in a little bit deeper into this. But what it turns out is that this is what you need to give it. You need to give it these two quantities here for the normal distribution. You give it location and scale. Now, location equals 0 by default and scale equal 1. That this is location. The scale is 1. And then you dig in the documentation. You figure out that that's what they're meaning. I'm going to spare you that thing. And I'll try to document those for you on how to use them as we build our knowledge with probability distributions. But the point is, here I want to create a normal distribution with a mean value of mu and a standard deviation of sigma. Okay, so I'm specifically giving it the keywords, all right? Now, when you create this, it doesn't create a function yet. It doesn't create a Python routine or anything like that. Internally, it creates an object on which you can call an object that's based on the normal distribution and that you can use to create a PDF, a CDF, get the variance, expected value, mean value, and so on. And this object that we create here is actually going to be a callable, an object that I can call. So I don't want to have to track to call this all the time, so I'm going to store this in a variable, okay, that I can call later. Right, so what I'm going to do, I'm going to call this norm distribution. This is my normal distribution, not yours. Well, yours too. Distribution, normal distribution. Okay, so now I packed all of this in a Python. That's what's so cool about Python. This is not a value. This is storing an entire object. And then whatever I want to call on the normal distribution, I want to call the PDF or the CDF or an expected value. I just call them on this from now on. Okay, so I'm mapping this variable called norm normal dist. I'm mapping all of this into norm dist, okay? All right. Now, when I do this, if I print norm dist, so print norm dist, it's just an object. It says this is a scipy.stats, infrastructure, RV, continue. I don't care. I don't care, okay? But it's an object. You still have to do something to use it. Okay. Now, before we go any further, I'm going to switch slightly. Once you are at this state, that's the only trick. That's what I was telling you how to use distributions. This is the only trick that we're going to use forward. So from here onwards, this is what we will do when we want to call a binomial distribution, a fish distribution, a Weibull distribution, the Poisson distribution, the fish distribution. So we will use this. But then once you are at this point, all the properties, PDF, PMF, CDF, expected value, mean value, variance, etc., all of those utilities you can just call them on this object. And I'll show you how. Let me show you the slide first. Okay. These are the key properties that we will call on this variable that we just created. Forget the first one, RVS, that gives us random samples. On the object I just created, I can call a PDF. I can say norm dist dot PDF at a given value x. That's going to give me the probability density value at that x value. I can call a PMF if this is a discrete distribution. I can call a CDF to give me the cumulative. I can call this PPF. We're going to learn about this later, okay? But we're going to learn it today or Thursday. I can call the mean, the variance, the standard deviation, and I can call the expected value on any function h of x, okay? This is does all of that for you. I tried to do this lecture in NumPy. It took me a couple hours to code all of this up, because to do the CDF, I have to do, if you remember quadrature, numerical quadrature, I had to do a quadrature formula on an infinite bound from minus infinity or semi-infinite support, okay? And to do this, what's called the PPF, I had to do an inverse function. So NumPy becomes very complicated to do. You'd need a lot of numerical methods to do it with NumPy. We're just going to use SciPy. They do it for us. Okay, so let's come back here. So now based on what I showed you on the slide, I can simply call, if I call norm distribution, okay, if you type in this period to access the what's available. If you press tab, it's going to give you a bunch of options. So let's start by computing the mean of this distribution. What do you think the mean should be? 10? What do you think it should be? We created a normal distribution with a mean value of 1.5 and a standard deviation of 2. What do you think the mean should be? 1.5, right? So if we're doing this correctly, when I call this function, it should return 1.5. Okay, beautiful. All right, so let's look at the standard deviation, STD. It's 2, exactly 2. The variance, if I call the var, which is for variance, so if you type in here, if you type in dot var, okay, it's going to give me 4 because that's sigma squared, okay? Now if I call the PDF, I need to give it a value. It's going to give me just the probability density at a given value. Say PDF at 1, it's going to give you 0.19333, right? Now I'm going to use this feature to make this plot. So what I'm going to do now, I'm going to do plt.plot. I'm going to take my x values. I'm going to do my norm distribution dot PDF at x. Okay? So I'm going to plot the PDF or the probability density value at each value of the x that we plotted. And this is what you get. A few lines of code, you're done. Okay? Okay, so let's experiment with this a little bit. I'm going to move this up here so that it's faster. We can plot things faster. Okay, so this is one with a mean of 1.5 and standard deviation 2. If we reduce the standard deviation, it's going to make it more narrow. So let's go to 1. Okay, now this is a standard deviation of 1 with 1. You go to 0.5, You see it gets getting narrower and narrower. Let's move the mean to -1. Okay, it moved it to -1. Let's move it to -3. It's moving the mean to -3, right? So that's all you have to do to access a normal distribution, okay? Now, the CDF is what you want to calculate probabilities. Agreed? Because that's going to give you the cumulative. And with a continuous distribution, you only can work with intervals, right? So let's say you want the probability that the x value is less than -2.5. All you have to do is go, instead of doing a numerical integration, you would go norm distribution dot CDF, and you give it -2.5. Now, what is the value? It's 84%, so that's the probability that x is between -infinity and -2.5, and it's essentially the integral of -infinity to -2.5, the area under that curve, okay? Cool. It's the cumulative density function, is the integral. It's the probability that x is between -infinity and -2.5, the definition of the CDF, okay? Okay. Are we in sync? Okay, great. Now, let's switch back to our slides. Okay. So I will add, eventually we're going to be needing these things, like you can get the kth moment, or expected value. Remember, it was the integral of h of x times the normal distribution times the PDF, right? So, and you can, all of these features, super powerful, very useful. You can just do them in one line of code, very useful. Okay, so next we want to talk, we're not done. There's still a lot to do with the normal distribution. We want to talk about the standard normal distribution, because scientists and engineers, we like to standardize things. Remember the symbol of the normal distribution, it's nx, and then mean value and sigma. When you take, so what does, when you see something like this, what does this stand for? It stands for a normal distribution with mean value 0 and a standard deviation of 1. Okay, that's the language we will be using. I will tell you in an exam, consider nx semicolon 3.5 comma 17. You should recognize that 3.5 is the mean of that normal distribution, and whatever 17 is the standard deviation. Okay. Now, this particular normal distribution is called a standard normal distribution. It is just a normal distribution, but with a mean value of 0 and a standard deviation of 1. And simply, it's given by this formula. When sigma is equal to 1, remember, you had a sigma here, and you had sigma squared over here, and x minus mu squared. When mu is 0 and sigma is 1, it simplifies to this very simple, beautiful formula. Okay, that's called the standard normal distribution. Why is it standard? Why is it super important? Remember when I said that the normal distribution in general is centered around its mean. Now, the mean could be 50, minus 17, etc. What if we move our coordinate axis so that it's centered around the mean? What will that do? It will make everything universal. It will turn any distribution into a distribution with a mean value of 0, because you move the axis to the mean value, you move the coordinate system to the mean value, and your standard deviation becomes 1 automatically. And here's the kicker. What's incredible about this is that you can transform any normal distribution to a standard form by simply defining a new variable. So you have a variable x that's normally distributed. It has a mean value mu, and it has a standard deviation sigma. If you do x minus mu over sigma and call that z as your new variable, then z will also be normally distributed, but with a mean value of 0 and a standard deviation of 1. Okay? So, and it's actually a theorem that if x is a random variable with mean mu and standard deviation sigma, then z is also in zx minus mu over sigma is also normally distributed, but with a mean value of 0 and standard deviation of 1. What you've done here This is the moving the axis to the center so that the distribution is centered at the mean value. And they normalize it by sigma, the width, so that everything becomes normalized. Mean value is 0, sigma is 1. What did we call this? Remember, we learned this in descriptive statistics in chapter 3 or 2. It was called the z-score. Z-scores are incredibly important because now with this simple transformation, I can unify all normal distributions in the world, convert them into a single normal distribution with mean value of 0 and a standard deviation of 1. Why is that powerful? Historically, people had a hard time calculating these. Can you imagine how hard it was to calculate them up, please, at the table? And I'll show you one of the tables I got here. Not exactly the same one that you have. Just actually, I can just pull the one from your table. Hold on. I know it seems like too archaic to use tables, but they are useful. All right. So your textbook will include in Appendix A this table. It just goes from minus 3.4 and all the way to 3.4. Okay. Now we'll understand why that is the case, and we'll work at an example together. So this would become clearer as we work this example together. So in other words, this is giving you the area from minus infinity up to the z value that you record. So these values in here in this table are the area from minus infinity until the z value that you've picked. Okay. So do some examples. Clear? Okay. The first example. Find the area under the standard normal curve to the left of z 1.37. So once you hear standard normal curve, immediately this normal distribution mean 0, standard deviation 1. You can use the tables. The tables are going to give you the cumulative distribution. So this is 1.37. So in this table, I'm going to have to look at 1.37. So because on the first column I have 1 decimal point, so I'm going to find 1.3 here. Keep going down. Okay, this is 1.3. Okay, this is 1.3 right here, right? And then we had 1.37. So this is 0.07 over here. So it will be this guy, right? If I can read correctly. Yep, 1.37 is going to be this guy, right? This guy, 0.9147 or 91.5%. Yes?
So this is just standardized for all normal.
For all, yeah. So you take any normal variable, you convert. We'll see in more examples. But what you do, the first step is to convert to a z-score to get the z values, to standardize everything. You look up the table, and then that's it. That's your probability, right? It's very powerful, super useful. Okay. Now these examples are just to look at the areas, just to give you some practice on how to use these tables. But yeah, if I'm correct, then this would be 94. Okay, so this is part of the table. Yep. So it's 91.5%. Okay. The area under the standard curve, etc. Now the area is nothing more than the probability that the z variable is less than 1.37. Okay. Okay. Another example, just to get you used to do this. Find the area under the standard normal curve to the left of z equal minus 2.03. I'll give you another example here, minus 2.03. So this would be minus 2.0. Okay, so what is it? Minus 2.0. And then where is minus 0.03? It's right here, right? So I have 0.0212. Okay, so this would be my area under the curve, very simply. Okay, and I'm going to show you this over here. So this would be this area under the curve. All right. Now let's take it up a notch. Now this is going to translate directly to probabilities. Because the area under the curve is the probability that your variable is less than this value. Okay? All right, so now I'm going to change things a little bit. Find the area under the standard normal curve to the right of 1.37. The tables, the CDF, give you the area to the left. Always, because it's the integral, it's the CDF, it's the integral from minus infinity to z. Okay, so you get the area to the left. What do you do? How do you get the area to the right? Method 1, you use the complement. You say because the total area is 1, so I take 1 minus the area to the left is going to give me the area to the right. So in other words, the probability that z is greater than 1.37, that means the area to the right, is equal to 1 minus the probability of the area to the left, or the probability that minus 1 minus the area to the left. Okay, so you can do that in the table. So you go look up the table and you get the probability. Method 2 is use the symmetry properties of the standard normal distributions. Now, be careful. Make note of this. All normal distributions are symmetric around the mean. But what we're going to do next, you can only use it on the standard normal distribution because we moved everything relative to the mean. So you cannot do this on an arbitrary normal distribution. It will screw things up. Now, because this is a symmetric distribution centered on the mean, the area to the right of 1.37 is equal to the area to the left of minus 1.37. Because these are mirror images around the mean. So this area is exactly equal to this area. So now, instead of looking up 1.37 in the table and doing 1 minus that, I just look for minus 1.37 and pick the value from the table and move on. Okay? Pretty neat. Now, of course, you can do this in Python. Let's do it in Python. Okay, let's do this in Python. Very simple. So let's see. So now first, I need to create a standard normal distribution. Okay? Standard norm distribution. I'm going to call norm. Now check this out. If I do this, this is going to, by default, give me a standard normal distribution. I hope so. Okay? That's my intuition. Let me see. Let's check. Standard normal distribution dot mean. Yes, it's 0. Standard normal distribution dot standard deviation, it's 1. Perfect. Okay? So just doing this, now obviously you can still say, you can put log equals 0 and then scale equal 1. But you don't need that because that's by default. You know how I guessed this? I remember when I was looking at the function signature, I noticed by default, they had location equals 0 and scale equal 1, which told me that by default, they scale this as a standard normal distribution. OK. Oops. All right. So now I can do standard normal distribution dot CDF of 1.37, which was an example we did earlier. Right? So that gives me the area, which was like exactly 91.46 from the table. Right? So it gives me the area up to 1.37. OK, so now let's do the area to the right of 1.37. We can do it one of two ways. 1 minus this, or standard normal distribution dot CDF minus 1.37. Agreed? So 1 minus the area to the left of 1.37 is equal to 1 minus the area to the right of 1.37 is equal to 1 minus the area to the left of 1.37. Area to the left of 1.37 is the CDF. And I'm saying that this is equal, this whole thing is equal to the area to the left of minus 1.37. Let's verify. Yes. Okay? Symmetry properties of the, yes. So the CDF always gets you the area to the left of the value you're looking at. Okay? What I'm saying is that we want the area to the right of 1.37. The CDF gives you the area to the left. So you either got to do 1 minus the area to the left, or the area to the left of minus 1.37, because they're symmetric. Okay, they're mirror images of each other. Again, look at this plot here. The area to the right of 1.37 is equal to the area to the left of minus 1.37. Okay? Similarly, this is another example. And finally, because we will be dealing with ranges, you're going to be doing probabilities between two values, two z values. So, you know, probability less than between z1 and z2, between like minus 1.68 and 2, for example. You follow the same procedure. You take the area to the left of z2 minus the area to the left of z1, for example, in this case, right? And you can get that working. Here's a little summary for you on how to use this. Area to the left of z0, you just look up z0. Area to the right of z0, you look up minus z0. Area between z2 and z1, you do area to the left of z2 minus area to the left of z1. And then finally, area below to the left of z1 and to the right of z2, you look up z1 and you look up minus z2 and you add them together. Okay, this is going to translate to a specific to an OR statement in probability. Right. This will get clearer with an example. Okay, as adults, okay, do you say adults or adults? Adults. Okay, adults. I used to say adults, but then one of my friends says adults. I'm like, this sounds cool. I'm gonna use adults, so you know, makes me feel different, but it's not. It makes me sound silly. Okay, as adults, our body temperatures are normally distributed. Normally distributed. So temperature follows a normal distribution with a mean value. So again, this is a PDF. What does the x-axis correspond to? It corresponds to just the population, like how many people in the population are within a certain temperature, okay? Well, sorry, the area. So on the x-axis, you're going to have temperature values. The PDF is going to be the density, and then the area under the curve is going to give you the population that falls in that category. Remember, it's a histogram, like a histogram. So they're normally distributed. We're giving the mean, 98.6 Fahrenheit, and a standard deviation of 0.73 Fahrenheit. Okay, so that totally specifies the normal distribution. This would be n x semicolon 98.6, 0.73. Okay, that's it. All right. Sometimes our bodies increase in temperature and we say we have a fever. Okay. Other times our body temperatures might drop to a place of hypothermia. Extreme fluctuations in either direction might signal, you know, issues or, you know, catching a virus or something. Okay. What percentage of healthy adults have a body temperature between 98 and 99? We have a bunch of other questions. So we start with the first question. So in other words, what's the probability that your body temperature is between 98 and 99 Fahrenheit? Okay? And that's why they tell you, you know, your body temperature is 98.6, but, you know, you could still fall within a good range. A lot of people fall in that range. I'm on the lower side, like my normal body temperature is around 96.5. I'm like, oh my God, you're saying? I'm like, no, I'm not sick. This is my entire life. I have, you know, a sloth style. Okay, so what is the percentage of healthy, you know, temperature? What's the probability that you would fall between 98 and 99? So we are looking to compute the probability of x, or the temperature, being between 98 and 99, right? So this is a continuous variable. You're looking at a range, right? So first thing I would do is just kind of try to plot that distribution. It's centered around the mean, that's 98.6, and we're looking at this area, like what is the area, what's the percentage of people between those two values. So you can use tables, and we can use tables or use Python. We'll be using Python, but using tables just for the sake of it. First, you need to convert to a z-score, because there's no table for temperatures and, you know, human body, whatever, right? But there's one table for standard normal distribution. So you first convert your temperatures to a z-score. You know the mean, you know the standard deviation of your variable x, or temperature. So you convert T1, which is 98, you convert that to a z-score. So the z-score in this case is T minus mu over sigma. It's 98, your temperature, minus 98.6, which is the mean, over sigma 0.73, and you get minus 0.82. So now, Z, in the Z world, that's a standard normal distribution with mean equals 0, and Z1 is minus 0.82, just away from that mean. T2 is 99. You convert that to a Z-score, and you get Z2 minus 0.55. Next, you jump to the table, and you get the value for Z2 from the table, value for Z2 minus the value for Z1 from the table. In other words, you're looking at this. Px less than 99 is equivalent to, let me fix this in the slide. My apologies. I should have put this here before. Let me fix this here. Is equal to P of, what were the Z values? Minus 0.55 minus 0.82 is equal to P. This is better. Okay. So this is our original probability, and that's equal to the probability in Z space that your Z variable is between minus 0.55 and minus 0.82. And then this is equal to the area to the left of minus 0.55 minus the area to the left of minus 0.82, and then you get these two values and you get 50%. Okay? Now, we can do this in Python as well, or Google Sheets. We'll do Python this time. So now in this case, because we have the power of Python, we can automatically use the original distribution, right? So go after the distribution with temperature. So let's verify that. So let me just convert this into human temperature problem. Okay, so method 1, method 2, method 1 in Python, use the original distribution. So you don't have to use the normalization, okay? So I'm going to say human temp distribution is equal to norm, and the mean value is 98.6 Fahrenheit, right? And the standard deviation scale is equal to 0.73. So that defines my normal distribution with those values. And now all I have to do, human temperature distribution dot CDF. We said what's the probability being between 99 and 98. So I'm going to take the area to the left of 99 minus the area to the left of 98. And that gives me 50.2%. Okay, 50%. So about 50% of the people have a normal temperature between 98 and 99 Fahrenheit. Okay? We can use a z-score as well if you want. So that's using a z-score. Method 2, using z-scores. Okay? Human. Actually, I already have it up here, the standard normal distribution, right? I'm going to do, so first let's convert to our z-scores. Let's compute our z-scores. So mu is equal 98.6. I should have done this better. Okay, I should have done this better. That's okay. Sigma is equal 0.73. And T1 was 98. T2 was equal to, what is it, 99. So that Z1 is T1 minus mu over sigma. And then Z2 is equal to T2 minus mu over sigma. Obviously, the right way to do it, you write a routine to compute your z-scores, okay? And then you pass it on to the normal distribution. Don't use Python as a calculator, okay? I'm allowed to do that. or if you're in a rush, you can do that. Okay, so now we have our z-scores, and we can print them, print z1, z2. Okay, so we get the same value we got in the notes. And now finally, I can use my standard normal distribution, which was this guy here, standard normal dot CDF area to the, no, hold on. Did I make a mistake in the slides? Yeah, I think I made a mistake in the slides. Z1, T1 minus mu. So this is going to be Z2, CDF Z2 minus standard normal distribution dot CDF Z1, and gives me the same exact answer. Okay? Math, man, rocks. It rocks. It's truth. It's incredible. Okay? So I made a mistake in the slides. I had a negative sign here. Okay, update that. Oops, still doing Python. So obviously, if you want to use the standard scores, you don't compute them like this. You create a routine, or you do this as a NumPy array. You know, vectorize the whole thing. Okay. You can do the same thing in Google Sheets. It's called norm.dist distribution, but you know, we're done with Google Sheets now. Okay. Question number 2. What percentage of healthy adults typically have, okay, now we start with the word games. Typically have either a consistently high body temperature of more than 100 or a consistently low temperature of less than 97. Okay? So what does that mean in terms of the curve? We're trying to find things on the tails. Okay? Temperatures above 100 or temperatures below 97. And the fact that you hear or, it means you're adding those probabilities together. Okay? So I always like to write it as a probability in math. P that x is less than 97 or x greater than 100. You can put equal sign, doesn't matter. These are continuous distributions, they're the same. So we're looking for these two areas, and we need to add them up. Okay? So now when you're doing table lookup, obviously, this is easy because you just look up the z-score that corresponds to 97. For this one, you have to do the negative of the z-score. Okay? So we'll do these z-scores just for practice. You convert to z-scores. T1 97 converts to minus 2.19. T2 is 99. Sorry, this should be T2. So what happens when you're building slides when you're driving? Okay, Z2 is 1.82. Sorry, like I'm like waiting for McDonald's. Like, you know, my son we're waiting for dinner from McDonald's. Like, I just grabbed the laptop. We gotta build some slides before coming to class. Okay, so the probability that either this or that convert to z-scores. This is equal to the probability that you are less than minus 2.19 or greater than 1.92 in z space. Okay, this one is easy because it's area to the left. This one is area to the right, which is equal area to the left of 1 minus 1.92, and that gives you 4.2%. Okay, only 4.2% of the population are either running hot or cold. Okay. Now here's a couple of trick questions, and I'm showing those just for completion. Sometimes you'll see a question like this. What is the probability that a healthy adult has a body temperature? This is the key question. What is the probability that something differs from the population mean by more than 1 degree or by more than one value? Okay? So you're going to see two things. Differs by more than or differs by less than. Those two things, and those are going to mean two different things. When you say differs by more than something, you're talking about areas in the tail. Okay? So in this question particularly, what's the probability that you differ by more than 1 degree from the mean? So you're looking at 1 degree to the left and 1 degree to the right of the mean, and then by more than that. Okay? So those would be your two areas that you need to add them up. You convert to these scores as well, and you add them up. So the more differs by more than 1 Fahrenheit means it's an OR statement. You're adding areas in the tails. Okay, the flip side of this problem is what's the probability of having a body temperature that differs by less than 1 Fahrenheit from the mean. The keyword here differs by less. You're talking about a closed area over here. So in this case, less than 1 degree from the mean. This is 1 degree on either side of the mean. We're looking at everything between the mean minus 1 and mean plus 1. So this becomes an AND statement, and you're adding those probabilities. Well, not adding them, you're just doing this area in this interval. Okay? So keep that in mind. I hate trick questions in statistics and probability, but just remember this. Differs by less, it's an area in between. Differs by more, you're adding the two tails. Okay, so let's take a 4-minute break. Let's continue. Let's resume. All right. So next we are going to look at what we call z-scores in reverse or reverse lookup. And the situation is interesting because this asks the opposite problem or the inverse question that we're used to ask. So far we've been asking what is the probability that the body temperature is between this and that, or etc., right? In this situation, we're going to ask the opposite question. What temperature corresponds to 85% of the population? Okay? So we say this is reverse z-scores or reverse lookup. Okay? And it's not that complicated. With the tables, you can find the answer pretty quickly, or we will use in Python the PPF that I referred to earlier. This is where this comes in handy. So here's the situation. The body temperature of adults are normally distributed between, with a mean 98.6 and a standard deviation 0.73. What temperature corresponds to the 85th percentile? And these are useful questions, right, to ask. So in other words, mathematically, this is asking the following question. Find A such that probability that x less than A is 0.85. Remember, 85th percentile is 85% of the data falls below that value. Okay, so we need to find A such that the total area under the curve is 0.85. So you could do a reverse table lookup, and you go jump on the table. So I'll show you. You can go, oh no. Okay, so you can go on the table, and we said 85th percentile. Okay, so we're going to start with a standard normal, and then we have to go back to the temperature distribution. Okay, so starting with a standard normal distribution, I need to find a value where here there's 0.85. Okay, and if I start scanning, you see the values. We're getting close. We're getting close. We're getting close. There you go. There's 0.84 over here, and there's 0.85. I'm going to take this value. So it's somewhere between these two values. I have 1.03 or 1.04. You could take the average. You could say it's 1.035, or just take 1.04. And that's the z-score. That's the z value where the 85th percentile occurs. Okay? Okay, great. But we haven't answered our question yet, because our question is, what is the temperature that corresponds to the 85th percentile? Well, easy. The z-score for the 85th percentile is 1.04. Then from that, I can deduce the temperature that corresponds to the 85th percentile. And I put the formula for the z-score. Z is temperature minus mu over sigma. I have mu, I have sigma, I have z, and I can solve for T. It gives me a temperature about 99.36 Fahrenheit. 85% of the people have a temperature of less than or equal to 99.36 Fahrenheit. Okay, we can do this in Python as well. And we can do it either with the z-score or directly on the distribution itself. We'll do it on the distribution itself. And the way to access this is to use what's called the PPF. So if you do human temperature distribution, you do PPF. What is the PPF? It stands for power percent function. some percent function, whatever it's. I don't know why they name it like that. But this is essentially, you're looking up the temperature value that corresponds to an area under the curve, okay, from minus infinity to that value. So the argument for the PPF is going to be an area under the curve from minus infinity to whatever temperature value we're interested in. In this case, it's going to be 0.85, right? And if I do this right, it gives me 99.35 Fahrenheit, okay, consistent with our answer from the table, okay? Reverse lookup, okay? All right, so let's go back here. We'll do a couple of z-score examples. I have some notes here for you on how to do this with a Google Sheets or Excel or SciPy.stats, which we did right now. Okay. Another question. Let's assume that the length of newborn babies in the US are normally distributed. So it's a normal random variable with a mean length of 20 inches. Can you imagine they're so tiny and cute? Yes, 20 inches and a standard deviation of 1.2 inches. What is the minimum length that a baby could be and still have a length among the top 25% of baby length? That's a mouthful. Essentially, we're asking what is the length of a baby, the height, how tall is the baby, such that he is in amongst the top 25% of babies in the US. Okay, so we are looking at. Okay, so hold on. What is the minimum length a baby could still have length that is among the top 25% of the baby? So if we want to find the minimum length of the top 25%, we can simply find the value of the 75th percentile. Okay, so over here he's taller than 75% of all other babies. So this is the same as the area under the curve with 0.75. So you can look that up in the table, find 0.75, find the z-score, and then from the z-score deduce the baby length, or you could do it also in Python as well, okay? With that, I think I'll leave the rest for Thursday. Will be a short discussion on approximating a binomial distribution with a normal distribution, okay? There will be a quiz on Thursday, and things are gonna get a little bit harder, all right, as we move on. Okay, so try to keep up the meaning of CDF, PMF, PDF, integrals, expected value. You need to know all of those, okay? Thank you so much. All right, Godspeed. 1 second. Let's begin. Last lecture of the week. So, headed to a weekend. Today, I want to finish with continuous distributions. There's one small section that will become relevant for the next chapter, which we will also start today. I hope to finish all of it today. It's relatively short, but we might not finish it today. Last time, if you remember, we left off with this example about the baby height being the question was, what was the baby height that was the largest, the smallest baby height that is still in the top 25%. So in other words, we're trying to find the edge of the 75th percentile or the third quartile, and we were able to do that with z-values, etc. You know all of that now. The last item we want to discuss today with continuous distributions, there are obviously more distributions than the normal distribution, but they all operate the same way. They have certain properties like a mean and standard deviation. Sometimes those have closed form analytical solutions, sometimes they're not. But the normal distribution stands as one of the most important ones. That's why we focus on it a lot. The next thing that is going to be important for us as we move forward is tying the binomial to a normal distribution. And it turns out under certain conditions, we can approximate a binomial distribution, which is a discrete probability distribution, with a continuous normal distribution. How's that going to work? Let's see. So if you remember, the binomial distribution counts the chance, the probability, it's a probability mass function. So it counts the probability that a certain number of successes, X, will occur. And the conditions is that the experiment consists of a fixed number of n of identical trials. So you're flipping a coin 50 times. Each trial is independent of the others, and there's only 2 possible outcomes per trial. Remember those conditions for the binomial. There's either success or failure. And you define success however you want. So you could say, you know, success is passing the course or success is failing the course. It's up to you however you want to, because it changes the wording of the statistical and probability question, but the answer will be the same. And each trial has a probability of success P. So let's say your success is landing heads, and you have a fair coin, so the probability of success is 50%. If it's a biased coin, maybe you have 40% probability of success, then P will be 0.4. And you count the number of successes in n trials, okay? Now, if the following conditions are met, that the number of trials times the probability per trial is greater than or equal to 10, and if the number of trials times 1 minus P, or the probability of failure, is also greater than 10, so if you meet those 2 conditions, then we are able to approximate the binomial distribution with a normal distribution. It's an incredible result, very helpful result. We will see that in the next chapter. Now, this normal distribution is going to have a mean of n times P. So that's the number of trials times the probability per trial, right? So if you think about that, a normal distribution is a PDF. The mean value is essentially going to be equal to the number of attempts times the probability of success per attempt. Now, the standard deviation is going to be square root of NP times 1 minus P. We're not proving these things. I'm not interested in developing proofs for these things here. These are results that have been well documented, and we will be using those. Okay. However, there is a problem. The binomial distribution, so this is if these conditions are met, then you end up with a normal distribution with mean NP. There's a little typo here. This should be n. Hold on 1 second. Square root of okay. Oh, actually, there was no typo. My bad. Okay. Yeah. So don't confuse the standard deviation. Don't confuse the standard deviation with the condition that n times 1 minus P. That one always confuses me. Okay. Hold on. This is right. Okay. So don't confuse the condition that n times 1 minus P is greater than 10 and this standard deviation or variance NP times 1 minus P. Okay? So don't confuse those two. So this is our path forward. We're going to approximate a binomial distribution. If it satisfies these 2 conditions, we can approximate it with a normal, mean value NP, and standard deviation square root of NP times 1 minus P. There's a problem. There's a problem. The binomial distribution is a discrete probability distribution. But the normal distribution is a PDF, and it only operates on intervals. So what does it mean when I say binomial distribution for success, 5 successes? How does that translate to a normal distribution at 5? You can't apply the normal distribution at 5. It's going to give you a PDF. It's going to give you a density. It's not going to give you a probability, right? So we need an interval equivalent when we go from the binomial to the normal distribution. And to do that, of all possible options, we do what we call a continuity correction. So if you're looking at a specific probability, specific event in the binomial at x, let's say the probability of getting 10 successes, all right? When you use the normal distribution to approximate that, you would be calculating the area under the PDF between x minus half and x plus half, right? No questions asked. That's called the continuity correction. You convert that singular value from the binomial into an interval under the PDF. Now that interval, you can compute the probability for that interval as a cumulative probability, right? Or, CDF of x plus 5 half minus CDF of x minus half. Okay? So let's do an example to fix these ideas. First example, antibiotic therapy for acute maxillary sinusitis. That sounds gross and scary. Inflamed sinuses. Has a clinical cure rate of 90% in patients. Okay, so that is going to give us the probability of success, right? That's going to be P. Use a normal distribution to estimate the probability that the antibiotic therapy will be successful in more than 100 patients out of 112 patients diagnosed with acute maxillary sinusitis. So this is a binomial distribution because we have 112 trials and we're looking for the probability of success at 100. All right, with the probability of success, in each trial, the trial is giving the antibiotic. Is it going to cure you or not? Curing you is success, 90%, 0.9 probability. And so we can use the binomial to get the answer, but in here we want to use the normal approximation to get that. So I have some of the animations are off, but first we start by verifying that we can use a normal distribution to approximate the binomial. We have two conditions. We have n is 112, p is 0.9. That's the success of the antibiotic. So NP is 100.8. It's greater than 10. And n times 1 minus p is 11.2. That's also greater than 10. Now, some people still apply it when those conditions are greater than 5. And that's still okay. Sometimes if you're in the gray zone between 5 and 10, try it and see what happens. Otherwise, just use the binomial. Okay? So when those conditions are met, we can apply the normal distribution. And again, you might ask, like, why are we doing the binomial? It's not like necessarily easier to compute than, why are we doing the normal? Is it easier to compute than the binomial? Well, kind of, right? Because we can use z-scores and tables for the normal distribution. There's only one standard distribution for all cases. So it tends to simplify things. But what's more important is going to be related to the next chapter and statistical inference. We want to get everything to be represented by a normal distribution. Okay. Step 2, build that normal distribution. In other words, what is the mean and what is the standard deviation for that normal distribution? We get a mean value of 100.8 and a standard deviation of 3.17, and this would be our normal distribution. Now, you could go and just call your normal distribution the non-standard one with your code, with Python or Google Sheets, or you convert to z-score in a table. That's up to you. Step 3 is we implement a continuity correction. So we're looking for the probability that the antibiotic therapy will be successful in more than 100 patients. Okay, so we know in the discrete case we are centered at 100 patients. Our continuity correction is going to tell us add and subtract a half a patient. And so our interval in the continuous distribution is going to be between 99.5 and 100.5. Now, we're not looking at the probability on that interval. We're looking for the probability that it will be successful in more than 100 patients. Okay? So we're looking at a bigger area under the curve. Okay? So let's see how that works. So once you have that continuity equation correction, you draw the interval on the normal curve and identify where your probability is going to be. So as far as I'm concerned, 100 is now this interval. It's not a point anymore, it's an interval because we applied that continuity correction. And when we're asking, we want it to be successful in more than 100 patients, so I'm not going to include that interval in my calculation. If they said if at least 100 and more, then we would include the interval. But here I'm not including it. I want anything beyond that interval. And so when I apply the normal distribution, I have to go to 100.5 at the edge of that interval. So be very careful with these. This continuity correction can mess things up a little bit, okay? It's not going to be the end of the world if you include the interval, but to be precise for the statement, this statement asks for more than 100, not at least 100 and more, okay? So then the process is simple. You convert to a z-score, you get minus 0.09, and then like we did last time, the probability, this is the area to the right, that's of minus 0.09. That's equal to the area to the left of 0.09. That's the mirror image, and gives you a 53% chance of success. So, you know, the probability that the antibiotic is going to be successful in more than 100 patients is, out of the 112, it's about 53%. Okay? Okay, this one applies to you. After you forgetting to study for your statistics test next week, 2 weeks from now, you believe that you only have a 25% probability of answering any given question correctly by randomly guessing the answer. So you didn't study. You're just going to come and randomly guess. Okay? And you think you're going to have a success rate of 25% at guessing the right answer. Okay? Based on years and years of not studying and just kind of trying your hand at different exams. Okay? So you know that. And now your test includes 50 true or false questions. And assuming that your estimate is correct, so yes, 25% success, use a normal distribution to estimate the probability that you will miss no more than half of the questions. So in the worst case, you're going to miss 25 questions. Worst case scenario, you're going to miss 25 questions randomly guessing the answer. So let's see what's going to happen. Okay. So forget about the, let's just start from the top. So step one, verify that we can use a normal distribution to approximate the binomial. Okay. So now here the wording is interesting, and we can approach this in two different ways. They will both give the same answer, but the questions can get kind of entangled. The wording can get entangled. So you could define success as getting the answer correctly, and then P is 25%. But because the question is asking for missing a question, so I'm going to define success as missing a question, because that makes it easier to reason about this statement here. All right? Now, missing a question has a probability of 75% of success. So you have a 75% chance of missing a question. And so I define n equal 50, and P is 0.75 because I define success as missing a question. And that's how they do it in the book, and I think that's nice because it allows you to change your thinking about what success could mean. You can define success however you want. Okay, and I did it the other way around, it gives me the same answer. NP is 37.5, so that condition is met. And n times 1 minus p, there's another typo here. See, I confuse that all the time. NP times 1 minus p. It should be n times 1 minus p is 12.5. And that gives us the conditions that, yes, we can use the normal distribution as an approximation, okay, because both of these numbers are greater than 10. Step 2, you build the normal distribution. By that, I mean get the mean value, get the standard deviation, and this is our normal distribution. It has a mean 37.5, standard deviation 3.06, okay? Now, step 3, apply the continuity correction. We're asked the probability that you will miss no more than half of the questions. So half of the questions, that's our point. And we have 50 questions, so half of those is 25. So our x value on the binomial would be equal 25. When we switch to the continuous normal distribution, we define an interval centered at 25 and half a question to the right and half a question to the left. So x is between 24.5 and 25.5. Okay? So now, with that continuity correction, we draw the interval on the normal curve and we identify that interval. Okay? Before you identify the area, this interval now means to me 25. Okay? That's my 25 in continuous world. All right. So now we're being asked, so remember the question is, the probability of missing no more than 25 questions. So 25 is going to be included in my probability calculation, right? So I need to include the interval in this area. No more, it means I'm capturing everything to the left. Okay? I'm capturing everything to the left, but my interval or my point on the continuous probability is 25.5. Okay, so I need to find the probability that x is less than 25.5 in the normal distribution. You convert to a z-score, you get minus 3.92. Okay, now I want to do something here. I want to pull a table, Suppose you're using a table. Let me see, find the table. Okay, so we had minus 3.92, right? Minus 3.92. Now, if you go to the table, move to Creston. If we go to the table, you notice the z values, they start at minus 3.4 and they end at about 3.4 as well. Okay? Now, if you look at the probabilities at z equal minus 3.4, so this would be the probability to the left of that point. They're almost all 0 because you're like so far on the left tail that there's hardly any area to the left of minus 3.4. Even worse for minus 3.92 because that's even further to the left of minus 3.4. So the fact that it's not in the table means it's 0. Okay? So you can say from the table, my probability of p is less than minus 3.92 is equal to 0. You can run it in Python or Google Sheets, gives you 4 times 10 to the minus 5, some number like that, but that's practically 0. Okay? So then you could say the probability of missing no more than 25 questions out of your 50 is approximately 0, so you will likely fail the test. You're going to fail the test. Okay? Okay. And this would end it for continuous probability distributions. This will be on your exam.